Hello everybody, this is Gigaraptor back again with some tutorials finally, and today we'll be doing physics. So this particular sub-series, which is about mechanics and Newton's laws and such, is aimed predominantly at those doing AS physics and the M1 module for AS maths, or A-level maths in general. However, if you're doing AP physics, I believe it is in America, I don't know, someone will probably correct me in the comments. It will probably apply here, and probably any good sort of physics curriculum around the world should probably have details from this in the second tutorial on it. So today we are doing the first two laws of Newton. So Isaac Newton was a great scientist born in the 17th century, and he basically created this idea of gravity for the first time, although before that Aristotle had some sort of idea of mechanics, although they weren't really accurate to what actually happened. And Newton looked at this and thought, well, hey, this can't possibly be true, and created his own model, which we use to this day, of course, because if we didn't, why would I be teaching it? So it basically consists of forces. So if we draw how Newton measures forces is in newtons, obviously. So if we have our shape over here, if we draw a centre of mass, how you would do forces with the Newtonian model is you'd like have some down here or something. Say, I'm not going to bother using the fill tool, so we're going to go 2g newtons, which means 2g, and we might have another one off here or something, just to give you a rough idea of how these forces work. So first law, Newton's first law. It's really difficult writing this with a mouse, as you can imagine. So all that Newton's first law states is that if the resultant force is equal to 0, the acceleration must be 0. That's all it states. However, what it is important to bear in mind is that just because acceleration isn't 0 doesn't mean that v is 0. Velocity remains constant. Only acceleration becomes 0. So, for example, if we were to have a shape here in equilibrium, so I assume you know what resultant forces mean. Resultant force is essentially the sum of all the forces is 0. So if we were to have a shape with a force applying 5 newtons this way, and we were to have 5 newtons this way, F-res would be 0, because 5 minus 5 equals 0, as you can imagine. And the same acts in the same direction as well, and we'll move on to calculating other things in a later tutorial. So, because F-res is 0 newtons, as we can see here, that means acceleration must be 0 meters per second squared, because it is a vector. We'll move on to that in another tutorial. I'll explain that. However, this doesn't mean that if there was already velocity built up on this object that it isn't still moving. It will just move at a constant velocity. However, the second law is sort of elaborates more on general rules, because like when you look at things, there won't always be 0 newtons. It's quite rare, because regardless of why things might appear to be like completely stationary, they're probably absolutely tinily slightly moving. So like for example, the plates below us, they don't appear to move, but they do slightly, I think by something like an inch a year. So no resultant force is quite rare. So now I'm going to go on to second law. And all this states is that the resultant force is equal to the mass of the object multiplied by the acceleration of the object. I really should have used a lowercase a on the other one, but this is what we generally use to show acceleration in an algebraic context. Same with maths. Now, if you've done GCSE physics, you're probably used to just this F. However, that's wrong, because the F just means any force on an object whatsoever, while this subscript here, which means the letters below it, res here, represents resultant. So if we were to, just to add this F-res here would let people know that you mean the overall force applied to an object rather than just one force. So let's come up with an example of the second law, we're just going to write it up here for those who need reminding. Just, you might need to remember it. It's not like it's anything important for any sort of exams or anything. It's not like it's the basis of a lot of our physics. Just remember this formula anyway. So, say we have our object here. Say it's a circle. We're going to mark its centre of mass because that's where you're supposed to draw forces from. We're going to say this has a mass of 2 kilograms. Understand? We've got 2 kilograms, right? This should be like this. We can kind of get into the third law thing later. We'll get onto the third law in the second tutorial. But just so you know, this is 2gn. And up here, this is because of third law. We'll cover it in more detail in the second tutorial, but it's important to put this here. We're going to have something called r, which is, well, if you know the third law, you know what it means. So, say we have applied a force to this circular, well, this semicircular, a really crappy circle here. Say we've applied, say we've applied 20 newtons of force here. Alright? We see this, right? And in the opposite direction, we have, say, 10 newtons. One thing I should probably say is note how I've coloured in these arrows. If we're going to do it like that, that will denote a force. So if I do this, I should probably use the fill tool, but from what I recall, this is just velocity. And if we do it like this denotes acceleration, because it is a vector and has 2 arrows. So that's acceleration. So if we're going to derive acceleration from this. God, I draw like Stephen Hawking. So, alright, so we're going to find x. So this is important because we see that acceleration here isn't, like, acceleration is over here, not over here. So we're going to just reorganize our equation here. So we're going to go acceleration is equal to our resultant force over our mass. Because acceleration multiplied mass equals force, force over mass must equal acceleration. This is GCSE stuff, you should know this. If you haven't, I suggest you go over your GCSE stuff. So to find x, we first need to derive our resultant force. So vertically there's nothing for third law, we'll go over that later on. But horizontally, we're going to do 20 minus 10, because the 10 is acting in the opposite direction to 20. So that equals 10. So F res equals 10. So our resultant force is 10. So now we need to find the mass, which is obviously 2. So A equals 10 over 2. Therefore, A is 5 meters per second squared. Understand? Understand this? Why this is? Because 10 divided by 2 is 5. So that's a basic one. Now we're going to do one where we find just resultant force. So, say we've got another circle. Oh, actually, that one's really crap. Another circle like this. So, we're going to find resultant force in this one. We're not going to. I was going to do mass later on. So we're just going to call this 3g newtons. So that means it's 3 kilograms, basically, because the gravitational constant refers to newtons per kilogram. So we will have a force here. We'll just call it F. And we'll have one back here. And that will be 15 newtons. And acceleration will be 2 meters per second squared. Alright, so since F res equals ma, we can easily work out our resultant force here, because it's just 3 times 2 equals 6. in this direction, I should probably mention. Direction is important because acceleration is a vector, which we'll cover in the third tutorial. So we know that f minus 15 must be 6. Therefore, we're going to do 15 plus 6 to give us a resultant force. Well, this force here equals 21. So F equals 21 newtons. We understand? So, for those who don't understand, our resultant force is the total of the forces. I should probably put an R here. I'll put an R here. Pay no heed to how long the arrows are. It's really hard to draw them accurately, so I just draw in them quickly. Usually when you're drawing diagrams, the arrows will reflect the magnitude of the force applying in a certain direction. So, what was I saying? So, resultant force is acting in this direction at 90 degrees horizontally to the right, like that. So, so what F would be, since we've defined F res as 6 because of the 3 kilogram weight and the 2 meters per second squared acceleration, we would get 6 newtons, right? And since 15 is acting in the opposite direction of the resultant, one would assume that F minus 15, because that's acting in the opposite, would equal the resultant force, which is 6. So 15 plus 6, as you should know, is 21. Now we're going to calculate one with just a random mass. So we're going to have, that was actually a pretty good circle for a first draw. So we're going to go colour that in a little bit. Then we're going to have a force of, say, let's give us a nice big number, 50 newtons. And in the opposite, we're going to have 22 newtons. With an acceleration of 5 meters per second squared. And of course, we're going to write this formula up here again. I should really get a good graphics tab, because then it would look better. But anyway, so to define our mass, since mass times acceleration equals force, mass must be equal to the force over the area. You get that? Good. Because mass times acceleration is force, so force divided by acceleration is mass, right? So, in order to get mass, we must define our resultant force. So 50 minus 22 is 28. And then we're going to divide that by 5, as per here. So that means that mass equals 5.6 kilograms. Because 25 divided by 5 is, well, 25 divided by 5 is 5. 3 divided by 5 is 0.6, so 5.6 kilograms. Alright, I hope this cleared up some things. That was Gigaraptor's first and second Newton's laws examples. The next episode we'll be covering Newton's third law, which is slightly more complex and will probably have a similar sort of length to this. So, thank you for watching, and I will see you next time on the next episode. Goodbye.